Now let's focus on one specific type of chemical reaction, and that is ones that are they use enzymes. So enzymes are proteins that catalyze or stimulate a reaction by lowering the activation energy required for the reaction to proceed. So this really can ramp up the rate of reaction, sometimes by large orders of magnitude. And then what ends up happening is the enzyme at the end of the reaction breaks off apart from the substrates. So they can glom on, here's a good picture of it, glom onto the substrates that things are being used in their reaction, create this complex, the reaction happens, the product is produced, and then that product is released from the enzyme. The total number of amount of enzyme, so I should say the total concentration of enzyme is always conserved. If we try to use the same structure as before, as we have a substrate plus an enzyme produces a product plus an enzyme, so we have a chemical reaction where we take a substrate, an enzyme, and at the end we have products, and then that releases the enzyme back into it. That doesn't quite capture what we want it to capture. It doesn't quite capture our picture, because think about what happens if the amount of substrate increased. If we increase the amount of substrate in this reaction, according to the law of mass action, if S went up, if this goes up, so will B. And it'll increase. In fact, it'll increase linearly, because the K times the number of enzymes will be like a slope of how fast that changes. That's not what we happen. We expect this to be limited by how many enzymes there are to catalyze this reaction. So if once you use up all your enzymes, you expect the reaction rate to slow down. So we expect the rate to increase to some maximum value depending on how many enzymes there are. And this was observed and modeled first by Michaelis-Menten. So let's talk about that problem. So in the 1920s, Michaelis, who was a German biochemist, and Menten, who was a Canadian physician, decided to look at what happens when the enzyme really comes into play in a chemical reaction. And so what they've noticed was that a substrate combines with the enzyme to first form a complex, can form this new molecule, and then that molecule is what breaks down into the product and releases the enzyme back into the play. And so let's take that in consideration when we build our equations. So now let's build some equations for the change in each one of these concentrations. So we'll have a change in our S concentration, a change in the amount of enzyme, change in this complex, and finally a change in the product, which I'll do off screen here in a moment. So the change in the S, well, we have a chemical reaction with S in the enzyme. That happens at rate K1, so we're going to lose S by that chemical reaction. And we're going to gain S by the back reaction from C. So that's similar to what we saw in previous slides. For E, we're going to have also a losing of concentration by chemical reaction between the substrate and the enzyme. We're also going to gain some from concentration C breaking back down. But then also we're going to gain some part of C that becomes, from this complex, goes to the chemical reaction at a rate K2 and then releases this enzyme later on. So you kind of think of E, we have arrows going out, K1, so that's negative change. Arrows going into E from C going back, and then C going forward. And then C changes by our substrate with our enzyme. And then we lose, arrows are going out, with K minus 1 of C, and K2, some percentage of that same rate, which we're losing that concentration. And then finally we can do one last equation for the amount of product, and that will be gained from how much C is happening at a chemical reaction rate K2. So notice there is no other molecule for C to react with. It's just C breaking down into the product in the enzyme. So there's our 4 equations. They look pretty complicated, and so our goal next will be to try to reduce these equations into a smaller number of equations that we can then try and solve.